Dobro veče. Dobrodošli nazad. Lekcija 13.6. Integrals for mass calculation. Yeah, we'll have to go and talk about these integrals now. So, first part is this is a three-part lecture. We have to find the center of mass for very thin but long rod, which could be of varying density. So if you have a uniform density for, let's say, a long plastic stick, it's very easy to find the center of mass. It's in the middle of the stick. But then, if it has a variable density, the center of mass to balance out the stick is not going to be in the middle. And the calculus can detect that, and calculus can tell us exactly where the center of mass is. So we can start these calculations by first defining the mass integral, right, where the mass is the integral of density. So mass is going to be integral a to b of some density function dx. So now if the density is uniform, right, we can calculate mass easily. If the density is not uniform, we will be able to calculate mass again because we can integrate. So let's take a look at so this is mass. So now let's find where is the center of mass for 1D, meaning it's a very long rod, so the other two dimensions are negligible, and we can just focus on the length. So center of mass will be given, which, since we are only looking in x direction, right, center of mass will be the moment divided by the mass, where the moment is given as integral a to b of x rho of x dx, which is the spin around the point that we want to find. So now let's immediately take a look at the example for this, and then jump to double and triple integrals and be done. So here is let's say problem number 12. Doesn't really matter. The density function is given as 2 plus cosine x, and we are looking from 0 to pi. So we find the mass of the object first, 0 to pi, integral of 2 plus cosine x, don't forget parentheses, dx, which is 2x plus sine x computed from 0 to pi. Both sine for pi and 0 is going to be 0, so we all have 2 pi. So mass is equal to 2 pi. Kilograms, grams, slugs, whatever. Not pounds. Pounds are units of force, not of mass. Then we calculate the moment, which would be 0 to pi of x times 2 plus cosine x dx, which is now going to integrate 2x plus x cosine x dx 0 to pi. Now, how do we integrate this? Very good. Integration by parts. So we have x squared, and then we have integration by parts. So it would be x is going to be differentiated, cosine is going to be integrated. So it's just going to be x sine x minus the integral of sine x, which is negative cosine, so plus cosine x, and all of that from 0 to pi. Right? I hope. So the first term is going to die. We have pi squared. Both sine x of pi and sine 0, they're all 0, so that's done. And then cosine of pi is -1, and so I have -2. Right, cosine of pi is -1, and then minus cosine of 0, which is another -1. So I have the moment to be pi squared -2, if everything is okay. So the center of mass is going to be pi squared -2 divided by 2 pi. It's about 1.5. You can get the decimals. Now, it's really important to use common sense and make sure that your center of mass is within the limits of the problem, because if the rod is 0 to pi, let's say inches, that means that the rod is 0 to 3 inches or feet, whatever. So the value you get for the center of mass better be somewhere between those two numbers. If it falls outside, something is terribly wrong, because you can't have center of mass outside of the object. That makes no sense, right? So pi squared, that's 3.14 squared, that's roughly 10. 10 minus 2 is 8. 2 times 3 on the bottom is about 6. 8 divided by 6. So this is roughly 8 divided by 6. Call it about 1.5. 8 divided by 6, 4/3. So we're good. It's, you know, approximation says 1.333. I know it's not, but it's pretty dang close. And you know what? 1.3 is less than 3.14, so it's between 0 and 6. So it tells me that this should be good. So for one-dimensional, for the length, this is the one that you will technically never use. The ones that you are going to use are double integral and triple integral. So center of mass for looking at the area. So you have something flat like this, and then where is the center, right? Where is the center of mass? And then obviously 3D, which is what you guys will definitely use, because that is center of mass of three-dimensional objects. So let's go immediately into 2D, where we are considering area. So in 1D we consider the length. Now we're considering areas. Again, we are going to have our integrals. Our integral for the mass is going to be the double integral over the whatever region you have. Rho is now given as rho of x and a y as input, and then you have dA. So that's your mass calculation. And you also have now two moments, one in x and one in y direction, because as you can see, when you have a moment on x, right, it flips in y direction, and when you have a moment in y, it flips in x, right? So that's why they might look confusing here, but just remember that the moment is that spin, right? And I have the moment of x, and the moment of x is given as the double integral over region R y rho x y dA, and then my is the same thing, except now we have x there. And now we can find our x bar, which is you take the moment of y and divide it by mass, and then y bar is moment about x divided by m. So these are your formulas. There are 5 formulas over here. I'll put that on the cloud. And if you guys, as I said, if you guys are still confused, why is this mixed like x's and y's and so on, as I said, if this is the x direction, right? If my arm is x direction, you see how this wobbles in y direction? Do you see that? And if you say this is the y direction, this wobbles in x direction, right? So if you really want to understand that stuff, just stare at it for some time and take a 2D surface and then try to flip it around. So we're going to take a look at the shape. Now we would like to, exploit the symmetry here, because I hope that, it will be common sense that if you have something on the XY plane that it's symmetric in one way, and has a uniform density, you have to be very careful about that, okay? Because the non-uniform density can really change the game. But if you have uniform density, then you can exploit symmetry. Let me give you some examples on the graph. So first of all, if you have uniform density and you just have a rectangle that it's symmetric like this, the symmetry must be in the middle. That should be common sense. So this is not uniform density, but let's say if it is, I would just find where the middle is by intersecting diagonals, right? And that's it. But you can always see that if I put this in the middle, it's trying to flip this way, not uniform density. So now, let's say that you have a shape. We can come up with any kind of symmetric shape and then exploit its features. So let's say you have the triangle like this. Let's say you have a triangle like this. The interesting thing is that your center of mass, if it's uniform, must be along the red line. Probably somewhere in this region here. It's not going to be anywhere else. You are expecting it to be on the red line. Now, if it's not uniform density, it could be anywhere. Because if this, let's say, I'm going to erase this, but let's say this region here is extremely dense, right? Then your center of mass could be right there, depending on how heavy. Now, calculations will reveal that, because you get density function. You get the density function, and you also get, you see the geometry of the shape. Geometry of the shape gives you the limits. Density function gives you how the mass distributes throughout that shape. And then both of them together play the role of figuring out the mass, figuring out the moment. When you divide them, you have the center of mass. So you have to be on the lookout for those words on uniform density and so on. All right, so let's take a look at the example from homework. Now, guys, everything flies over here. We're talking about double integrals in polar coordinates. Why not, right? Don't discriminate. Be nice. We can have also polar coordinates pop in. Let's see, the region is bounded, so let's find the mass and centroid center of mass for the following thin plates assuming constant density. Awesome. So we'll do one with the constant density and one with the I guess variable density. So let's see what looks. You want to do ln x? Do you want to do 1 minus absolute x? Ln? So that will be 19. We have the region is bounded by y equals ln x. So region R is bounded by y equals ln x. It's also bounded by x-axis. And it's also bounded by x equals e line. I like to draw this so I can see, so I can set up integrals. You have to have a drawing so that you can do the shapes. So I know how ln looks like. X equals to e. And x-axis. So we are trying to balance out this region here. So mass is going to be a double integral of, and I'm just going to use rho because it's a constant density is just a number, like 7, okay, or 12. So I'm just going to call it rho, and I'll have rho in the moment calculation, and they will just cancel once I divide out, right? So I just put rho. You can also ignore it, but I like to put rho there. And then I'm going to work on this is dx, so it's going to be dy dx. X goes from 1 to e, and y goes from 0 to ln x. So remember that if you're using dx to be the boss, then the top and the bottom are going to be the limits of the dy. So to calculate mass 1 to e, we have rho y 0 to ln x. We still have dx. So this is 1e rho ln x. And then we have dx. Now we have to integrate ln x, and I'm not sure if you remember the integral of ln x, which is
really bad.
X plus x ln x. No. Anyone? Because you have to use integration by parts, right? I'm trying to remember. Is this x here for the
Yes.
yeah, it is, right? Because you can, yeah, I think it is. Yes, it is. But Alex will confirm that 15 times, right? Just type in Wolfram integrate ln x. That's it.
It's telling me it's x ln x minus x plus c.
X ln x minus, okay.
Plus c. Yeah, plus c.
Yeah, the integration by parts is a minus.
Oh yeah.
Alright, so we get rho, we plug in e everywhere, so that's gonna be e minus e minus plug in 1, that's gonna be 0, and then plus 1, So the whole thing just becomes rho. Nice. So ln of e is 1, so e times 1 is e, minus e. Plug in 1, but ln of 1 is 0, so that dies. And then plug in 1 and minus, so we get rho. Perfect. Now we're going to calculate the moment in either x or y, doesn't matter. So let's calculate moment in x. Moment in x is the double integral of rho y dy dx. Now the cool thing, guys, is that you will be recycling your limits all the time. You will be recycling the limits all the time, but you have to redo the entire integral because the structure, as you can see inside, is different, right? So now we have 1/2 rho y squared computed from 0 to ln x dx, and that gives me integral 1 to e of when I plug in ln x, I get 1/2 rho ln x squared, right? And then minus 0, and then we have dx. 1/2 rho is the constant, so you can kick that outside. And now we have to integrate ln squared x dx. What?
Wow, that looks terrible. All right.
So what do we get for that one?
ln squared x.
Put ln x in parentheses.
Yeah, I got it. Oh, hang on. I gotta make that normal. Wow. X ln square root of x.
X ln square root of x.
No, squared of x. That's square root.
Like this.
Minus 2 times parenthetical, is that the word? Evan's been using that. I like it. X ln x minus x.
Where's minus x? Is it in the
In the parenthetical. I love that word.
like
Is
this?
there a word? Yeah. Plus it.
So plug in e, that's 1, so that's just e. Plug in e, that's 1 minus e, so minus 2 times 0. Plug in 1, we get 0. Plug in 1, we get 0 here, but we get 1 there, so it's a negative 2. And we get e minus 2 over 2 rho. So now I can find, I calculated mx, so I can calculate Alright, cool. So I calculated mx, which means I can find the y bar, and that is going to be e minus 2 over 2 rho divided by, did we get rho or 2 rho? Just rho, which is e minus 2 over 2. Also, you can write 1/2 e minus 1 if you want to, whatever makes you happy. E is about 2.7, call it 2.8 to calculate easy. 2.8 divided by 2 is 1.4, minus 1 is 0.4. Right, so 0.4 on y. Now you see that makes sense. 0.4 on y makes sense. It's a positive number, and it's less than 1. It's between 0 and 1. This point here is e comma 1, because when you plug in e into ln x, you get 1 as the y value. So we better have y average somewhere between 0 and 1, and we got it at about 0.4. So we're cool. Now we have to find the x bar, which means we find my, and that one we expect to be between 1 and e. So it better be, you know, I don't know, 2.1 or 1.9, something like that. So we now do the second part of this calculation. We find my, which is the double integral. Again, it's the same integral except now we have x rho of x, x rho, and then we have dy dx and go from there. What were the limits? 1 to e and 0 to ln x, right? So we recycle because it's always the same region. So for mass and for both moments, always the same setup. That's why it's important to get the setup right. 1 to e. We have rho xy computed from 0 to ln x dx. That's going to be 1 to e. Plug in ln x for y, we get rho x ln x dx. You can kick rho in front of the integral if you want to. We have to use, again, integration by parts. So it's going to be can we do anything else? No, right? We have to use integration by parts. Is that true? So for the integration by parts, u equals x, dv equals ln x dx. Oh, we're integrating this one now. Let's swap them. So now du is going to be 1 over x dx, and v would be x squared over 2. So now what do I have? I have x squared over 2 ln x minus integral of x 1/2 x dx. Awesome. So density rho goes outside. We already have x squared over 2 ln x minus 1/2, so 1/4. So x squared over quarter. Computed from 1 to e. So now plug in e. We get 1, so that's e squared over 2. Plug in e minus e squared over 4. Plug in 1 that dies plus 1/4. So this is 1/4. So we have rho, we have 1/4, and then that's e squared up there, right? So that's 2 minus 1, so it's e squared plus 1. X bar is rho 1/4 e squared plus 1 divided by rho. These guys cancel, and I get 1/4 of e squared plus 1. Now e squared is roughly 10, plus 1 is 11. Quarter of 11 is, right, 2 point whatever. So it falls. It needs to be close, guys. The center of mass, I can actually, let me just try to get a good approximate answer here. So e squared plus 1 Oh, e squared is not 10. E squared is 7. About 7. So that's 8.4, and divide that by 4. We get about 2.1. And this one over here was about 0.4. E divided by 2 minus 1. It's 0.36, so about 0.4. Now, does the answer of 2.1 make sense? The answer is hell yes, because if you look at the shape right here, if you look at the shape, this is 1, this is E 2.7, so 0.4 should probably be right there, which is good for center of mass because there's a lot of stuff happening here, and then it dies off on this side. So 0.4 and then 2.1 sounds good, right there. As I said, if you are trying to, you want to use the common sense and make sure that your center of mass is inside the object. All right, that was problem number 19, I believe. Do we need to do one with a variable density that will just make integrals worse, or no? Or you can integrate. So variable density plates, they give, they just introduce density to make integration worse, but the setup and everything is the same. As long as you know geometry of the shape, you should be able to set up the sides. Move to 3D. All right, that's the spirit. Now we're going to peek into the object and find the center of mass. As I said, the aircraft, the car, whatever you are designing, the ship, you need to know where the center of mass is, because you don't want to build this multi-million-dollar cruiser or something and you put it in the water and just flips on the side and sinks. So you have to worry about these things, right? Weight distribution and everything else. Find the center of mass. So now we are going to have 4 integrals, right? Because we have 3 for all the moments, and then the mass one. You always have the mass integral. So mass integral will be the triple integral over region D of your density function, which is xyz now, dv. Now density function is here given as the xyz, but you can have spherical coordinates, you can have cylindrical coordinates. It's okay. Moments. We have a moment on yz, which would be the triple integral of x rho which gives us the x bar when you divide the moment yz by the mass. Then we have the moment on xz, which is the triple integral region D on y rho xyz. It's very systematic. Y bar is mxz divided by the mass we calculated earlier. And finally, the moment on y xy, which is the triple integral region D on z rho xyz dv z equals mxy divided by the mass. So those are the formulas, and as I said, be very careful about the shapes you have and calculations you need to do, because you might have to jump into cylindrical or spherical realm to solve the integral. Do the example of this. Like, we can pick the worst possible example and just burn the rest. But no, we have to start 57. Do have the review. With a smile. The smile. The fake one.
There's a smile.
Yeah.
Just light up for you. The answer is no.
That's why there are people that I can rely on to get, like, see, there you go. There we go. Who else? See? Plenty of people. They're always relying on you, right?
Hey, cool, free pencil. Oh, it's regular people.
Variable density solids, we'll probably cry with those ones, but that's okay. So let's take a look at 28. It's a constant density. We have a solid bounded by paraboloid z equals x squared plus y squared, and the plane z equals 25. So if I draw this, it's going to look like this. Right? It's a paraboloid. There we go. So now we set up our integral for the mass and solve that one first. The integral for the mass is going to be the triple integral. And we have our constant density rho. So we don't have a function there, it's just rho. And then dz, dy, dx, I guess. So is this something that it's appropriate to be used here? Dz, dy, dx? Oh no, you definitely look, you have z equals x squared plus y squared. So that's going to be one of the limits. That's definitely going to be integrated first. Any other suggestions? I'll wait. It's a triple integral. The one from yesterday. Cylindrical coordinates, very good. Cylindrical coordinates. So guys, we have to spot this x squared plus y squared. You don't want to end up working and cranking trig sub within triple integral. or a double integral. You can, but it's going to take you hours. So as soon as you spot x squared plus y squared, you immediately know it's going to be cylindrical. If you have plus z squared, spherical, right? So these are some of the things. So we are recasting now this integral into triple integral, rho, and then we have our string for cylindrical. Anyone remembers it? dz, r, dr, d theta. Okay, cool. So theta 0 to 2 pi, because it's the full paraboloid going around. The radius will go from where to where? Wait, why did they say z is z 5 or 25? Oh, z is 25. So 0 to, Nick, what did you say, 0 to? 5. 0 to 5. Because square root of 25 is 5. This is supposed to say 25 over here on the picture. Remember how we get the radius? It's the widest this can be, so radius is going to be 0, and then it's going to be one value, more, and then more, and then more, and then more, and then more, and the most it can be is 5. So it starts here as radius is 0, and the most it can be is 5.
So why is the radius not? Oh, it is. Never mind.
Yep. You have dr. And we also have z, and z clearly goes from 0 to 25, right? Because the bottom is 0 and the top is 25. So there's the mass integral. We compute this, so that's 25 rho r dr d theta. Now we're going to kick out 25 rho integral 0 to 2 pi, and when I integrate r, I get r squared over 2 from 0 to 5 d theta. I kick out, well, I have 25 rho, and then I have another 25 over 2, and then I have a theta computed from 0 to 2 pi. That will kill the 2, so it's 5 to the 4 rho pi. Right, because I have 25, that's 5 squared. I mean, we can calculate because it's 625, right? It's 625 pi, but 5 to the 4 I like it better because I can cancel better. All right, so that was that. Now the moment on YZ. Oh, first of all, it's a constant density. Exploit the symmetry. Do you see that when we do the moment on YZ, which is right for x, we have to get 0 at the end, right? Because the center of mass must be on z-axis. This is what we say radially symmetric, right? Because it's constant density. All of this goes to garbage if it's not constant density. But because it is constant density, we can utilize symmetry and clearly see that the center of mass has to be somewhere in the upper half of the shape, but must be on the z-axis. Must be on the z-axis because it's constant density and it's symmetric. So we are looking for answer 0019.4, let's say, just to throw out a number. So the only moment that we need to compute here is moment x, y, which is the triple integral with same limits and everything, but it is going to have a z in here, rho, and then we have our standard string dz, r, dr, d theta, and then all the limits as before, which is 2 pi and 5 and 25. So do the first integral, the inner one. Z, that will be z squared over 2 rho from 0 to 25 r dr d theta. That's 625 over 2, so 5 to the 4th, right? I'm not gonna do that. Over 2, kick that outside as a constant. And then we are integrating r now, so that's r squared over 2 from 0 to 5. D theta, which is equal to, now I have 5 to the 6th rho over 4. And theta, and then I have theta from 0 to 2 pi when I integrate, which is canceling this, so I have 5 to the 6th pi rho over 2. So z bar, the only one that we have to compute, is 5 to the 6th pi rho over 2 divided by the mass, which was 5 to the 4th pi rho. So pi's die, rho dies, 5 to the 4, we're left with 25 divided by 2, which gives me 12.5. I'm really not happy with this result because it's right in the middle. I don't like this result. So there is some kind of algebraic mistake somewhere. We need to get 18, 19, something like that. Because if the shape is like that, there's much more material of constant density on top than on the bottom. And there is a mistake somewhere. It's not by a lot, but obviously it's wrong because you cannot have it to be halfway. You know where's the halfway? This object. That in the center of this object is the center of mass if it's constant density. As soon as I shave some weight on the bottom and make it into paraboloid, the top is going to be heavier than the bottom. So the center of mass must move up. So that's, I definitely know it's the wrong answer, right? We have to figure out, I mean, if you're inclined to find where it is, what's wrong, something is wrong.
Maybe the limits?
No, limits stay the same across the problem for all integrals.
Maybe, is it in the first thing you did? You know, where you did 25 there, 25 over 2. You cancel with the 5 to the 4 pi. Yeah.
Up.
Yeah, 25 over 25 over 2.
But then I had 2 pi coming in, so 2 cancels 2, right? So 2 pi coming in for theta, 2 cancels 2, and you have 5 to the 4th rho pi. So that should be, it's probably some mistake over here with these. So you have a z squared over 2, plug in 25, that's 25 squared, which gives me 25, that's 5 to the 4th rho over 2, that's good. And then we have r squared over 2. When you integrate that, you bring in 5, then brings extra 2 5s, so now you have 5 over 6 over 4 rho theta, and then 2 pi. 2 pi cancels that one. Yep.
Flip side. Or, oh, it's even, so there's no answer.
Yeah, there is some calculation, so I don't see it where, but I hope you see that we are using cylindrical coordinates because the x squared plus y squared, you really don't want to integrate that using, you could, but you don't want to. You don't want to use the trig substitution, right, for that, so that's why we switch and make it easier in cylindrical coordinates. So I'm just gonna say at the end over here, fix it, so find where it is. Here. Not cool. All right. Need about 18, 19, you know, something like that for the center of mass of this one. Or maybe 17, I don't know. So there is calculation error. It cannot be there. Another example of this? Yes, no?
No, because we still gotta do some of 13.7.
Alright, so let's take 2-3 minutes and then swap to 13.7. No, 13.7 takes forever. Alright, so just figure out what went wrong here, find where it is and fix it. You're looking for the answer anywhere from 17 to 20, wherever it lands. And I'll see you all in 5 or so.